Welcome back. Let's knock off a couple of sections. These next two aren't too long. So, sea level change also affects what we see happening at the coast, which will cause hazards. More on that. We're building up to that. So, when we're talking about change in sea level, it actually occurs kind of a couple of different ways. The first is something called eustatic sea level. This is sea level changes due to changes of the volume of the Earth's ocean. So something's happening to the water. There's more or less water, volume-wise. And it's called eustatic sea level. So again, the amount of water in the ocean changes, the volume. This could be due to the overall shape of the ocean basins due to plate tectonics. It could be volume change due to climate change. So think of melting ice, adding water to the oceans, causing it to rise. That'd be eustatic sea level. But also something called thermal expansion. When things heat up, they expand. What's a good example of that? Think about if you're wearing a ring. This happens to me all the time. If I'm very active, if I get a little warm, my finger swells up a little bit, can't get my ring off. When things heat up, they expand. When metal heats up, it expands. When everything heats up, it expands. That's just a property of physics. The atoms get excited when you heat it up. You're applying energy to something, no matter what it is. Those atoms get excited and they want to spread out. So that material also spreads out. So thermal expansion of the ocean also occurs. So as the climate changes, not only does the atmosphere get warmer, the oceans are getting warmer. Because the oceans and atmosphere interact. Think back to last unit. So if the oceans get warmer, the volume gets bigger. It expands. You're not necessarily adding water, but the volume is getting bigger because the material itself is expanding. So if the volume of the water is expanding, sea level are going to rise. But the reverse of that is also if it gets cold. If it gets colder, material kind of shrinks up, and yeah, it would get smaller. So thermal expansion of the ocean, which is caused by climate change. That's responsible currently for adding about 1.38 millimeters per year rise in sea level. That's not much. So, I mean, we're talking, about a little more than the width of my fingernail. Maybe just a little bit thicker than the width of my the thickness of my fingernail. My fingernail, your fingernail is about 1 millimeter thick. So just a little bit bigger than that. So every year, just because the ocean's warming, that's how much sea level is rising, which is not a lot, but when you add that up over 10, 20, 30, 100 years, it becomes a lot. But that's only half of the measured sea level rise is due to thermal expansion. The other half is due to melting ice, melting glaciers, melting ice sheets, also caused by climate change. And that adds 1.37 millimeters per year sea level rise. So about almost half-half. So half is thermal expansion, half is melting glaciers, melting ice caps, melting ice sheets. So again, when things heat up, they expand. So these are some railroad tracks in some hot location, and they got so hot that the metal expanded and it had to buckle. If you ever driven across a bridge, before you leave kind of the hard land surface and you get onto the bridge, you'll see these kind of teeth. They're fine. They're not going to pop your tires or anything. These are thermal expanders. So since all material expands when it heats up, bridges are also built like this. So the edges of bridges, before it kind of hits the solid area on the one side of the bridge, they'll build this thermal expander in there. So if the bridge does expand, which it will when it heats up in the daytime sun, there's room for it to expand. Because if it wasn't like that, if this wasn't built in and it was just one solid piece of bridge, this would happen. And that means the bridge would crumble and fall apart. Things heat up. When things heat up, they expand. Whether it's a gas, whether it's a liquid, whether it's a solid. So again, the main causes of sea level rise, 1.38 millimeters per year is from thermal expansion, just because the ocean is getting warmer, and another 1.37 millimeters is coming from melting ice. Greenland, the melting of Greenland has the biggest part to do with that. Random glaciers around the world, and then the melt of the Antarctic ice sheet currently. So that's eustatic sea level. The volume of water is changing. But then you also have relative sea level change. This is global sea level changes due to change in relative distance of land to shore. So this could be due to something called crustal rebound. So once ice melts, then there's no pressure on the land. So due to plate tectonics and what's going on beneath the earth, that material could kind of rise up. Think about your bed. All right. As soon as you get up off your bed, it doesn't happen right away, but slowly, your bed begins to rise back to normal height. Or same with your pillow. Once you get up, the pillow kind of fluffs back up. Well, same thing happens with Earth. If there's an area that's covered by something heavy, like a big ice sheet or big glacier, if that material melts away, then that land below it doesn't have that pressure on it anymore, will kind of bounce back up, called crustal rebound. So if you're sitting in a city and all of a sudden the crustal rebound is causing your city to raise in elevation, well, relative to you, it looks like the sea level's dropping. That's not really the case. It's just relative from one thing to the next, it looks like it changed. During the last ice age, there's a lot of ice sheets that covered, for instance, North America. Obviously, with all that melting, that added water back into the ocean, but we're not talking about that. Over time, the crust itself is kind of raising up, and it still is in some areas. So it seems like, in some cases, the sea level might be dropping or not raising as fast, but that's just because the ground is also raising up. Plate tectonics, that can also change where one thing is relative to another, where the coast is relative to the ocean. A great example is an earthquake in Alaska in 1964 caused a portion of an island that sits right along the convergent boundary there to rise 10 meters. So it rose 33 feet. So it looked like the sea level dropped. Well, that's not the case. The sea level stood where it was. It was just the other part of the plate, just where the city was, where the island was, rose up. So it looked like the sea level dropped. If you're in an area where there's a lot of deposition of sediment, or the reverse of that, erosion or subsidence, where the ground is sinking, that can make it look like sea level is changing. Tides, when you're at the ocean, there's things called high tides and low tides. A lot of this stuff we touched on in my other classes. We're just briefly touching on it to get to the hazard discussion. But in any case, tides, some parts of the day, the tide's very high. It's very up close to the beach. Some parts of the day, it's further away. That has to deal with just the interaction between the Earth and the Moon and the Sun, but it makes it appear like the sea level is changing. Weather conditions can also cause that. Think of hurricane storm surge, can push water onto a coast. So it can make it look like sea level is changing. That's relative sea level change. It's not really, but something relative to your point of view is changing, causing it to look like sea level is changing. So here's a map of crustal rebound. So during the last ice age, a good portion of North America was covered by an ice sheet. That ice sheet has since melted away. Well, since that ice sheet has melted away, a great portion of North America is rebounding, this crustal rebound. Same thing in other parts of the world. Even Antarctica, as it's melting away, parts of Greenland as it's melting away. Those areas are rebounding upwards of 18 millimeters per year. That's a decent amount. That's about this much. Doesn't seem like much, but over time, an inch a year, 12 years later, your house is a foot higher than it was, 12 years ago. That can make a big difference. Here's an image of that island in Alaska that rose 30 plus feet, 10 meters. So you can see it looks like the sea level dropped, like where the shore was right up here. The shore was right up here. Now it's way out here. Well, it looks like the sea level dropped. Well, no, that's because the land actually rose up. In any case, so that's the first section, section 4. Section 3. Let's also talk about section 4. So, what regions are at risk to all of this stuff? Sea level rise, wave interaction, causing hazards that we have yet to talk about on the coasts. So here's an image of the U.S. We'll focus on that, where we do see coastal erosion, which can create things like landslides and a number of different things. So red is severe. The yellow-orangish is moderate, and the gray is relatively stable coasts. As you can see, there's not a lot of gray. But look, there's a little bit between LA and San Diego and San Francisco and kind of up on the Oregon coast. Little spots here and there, but for the most part, the vast majority of the coastal U.S. is all severely or moderately eroding, being eaten away. That's a big deal. That's a big deal. A major driver of that can be the type of rock that we have along these coasts. So yellow sedimentary rocks, clastic sedimentary rocks, sandstone, shale, things like that. Blue, also sedimentary rock, but limestone. So all these sedimentary rocks are very easily broken down, very easily weathered and eroded. Red, igneous or metamorphic rock tend to be a little bit harder, a little bit more stable. They're a little bit harder to erode. So really, that really only exists in a couple of places. Other than that, the coasts are very easily eroded because of the rock material that's there. Looking at homes at risk to sea level rise and just major storms. Obviously, the red, the worse it is. So it shows you homes lying less than 3 feet above mean high tide, so the average tide, in thousands. So when we're looking at dark red, we're looking at, for instance, Florida dark red, 500,000 homes. When we're looking at, Oregon and Washington, anywhere from 0.1 thousand, so that's 100 to 25,000 homes. There's a lot of homes, right? Louisiana, Florida, New York, California, these are obviously all low-lying areas, just like the other places on the coast, but they also have major cities that are very susceptible to sea level changes. And as you see here, a 3-foot increase in global mean sea level is very much plausible by 2100. That's less than 80 years away. That's, a generation or two away. What that means is, since 53% of the U.S. population lives on the coast, most likely 53% of people are really going to be affected by climate change and sea level rise in their lifetime. Again, 3 foot doesn't seem a lot, but that's the difference between having a home and dry and having a home partially underwater, thus destroyed. So it can mean a lot. We'll look more of that in lab. So we'll go ahead and pause here. When we come back now, we're going to start to talk and get into the nitty-gritty of the hazards. You got a little bit of background about the different types of coastal margins, active versus passive, near or away plate boundaries, how waves kind of shape the coast, how other factors can shape the coast as well. So when we come back, we'll actually look at and get into some of those hazards of all these coastal processes where land meets water. I'll see you back here in just a second.